How to find Haohua Deng from Duke who talk on Kato-Usui type extension of general period maps.
Thank you so much for the invitation. I really appreciate the chance of being a talk here, and also thank you all for coming. So this talk is based on my thesis in 2022, and I would like to present also my PhD advisor Matt Kerr in this problem. Okay, so let me introduce what are the basic objects I do in this topic. So in this topic, I'm looking on a general period map, which means, well, as the form of S2 gamma by T is a quotient of some period domain. Okay, so there, like, so we assume this S has a nice shape, is assume S is positive projective. And we assume that the boundary divisor of this S are no cosine divisors. So I just say this is I indexed by some, this I is an index. Okay. So what we are going to do is we want to find some theory to extend, for example, S in this ext means some partial extension, and this is becomes part of this S bar, such that for such a if we are extending some boundary strata into the original S, we can have a form, we can have a way to extend the original period map by, let's say, by X to some, well, the extension of the original quotient of period domain and some proper extended space. And of course, we want this like extended period has a significant geometrical Hodge-theoretic meaning. Well, so first, let me introduce like some very basic theories. So first is well, this is due to Griffiths. So with that I, so if I is the index set, and index is all of these boundary devices, and I T be the sub-index of I for which the corresponding monotony representation is the corresponding monotony operator Ti are finite. So we assume like so we take off like all of these devices we are corresponding to finite monotony. So in this case, it's a very classical result that because we know that this S, the original period map, can be extended to this locus, this boundary devices with finite monotony. So let's say S, well, ST, let's say this. And the image is still in the original period, the original quotient period map. So this is one of the most classical results. And second, we're talking about the Shafarevich Baily-Borel compactification. So this compactification is done for in some special cases where the B is a symmetric. Or say like so we say that B can be amplified, but phi factors through some locally symmetrical varieties. So then we use the is so if phi factors through some locally symmetric variety, we should actually still denote as gamma by D because otherwise you can just replace this gamma by D by the locally symmetric variety and factor through. So in this case, Shafarevich Baily-Borel might be like a constructed combination for a special case like so the upper single upper half space and Baily-Borel construct for general locally symmetric variety. So it constructs a compactification, let's say gamma by D, let's say SBB. So how about this compactification? So this compactification is canonical and projective, but however, that's a highly single. Usually highly simple. And one of the simplest example is SBB is the single upper half space. So this HG is associated with the single upper half space, like so, okay, cushion by ST. So if we take the SPB compactification of this single unbounded space quotient by SP2G, then it is just SQ union is all lower rank single unbounded space. So we have each level strata can be one single one. Okay. So this is something about Baily-Borel. Next is the toroidal compactification by Ash-Mumford-Rapoport-Tai. So compared to, so it also works for the locally symmetric varieties. So if this gamma by B is a locally symmetric variety, then we AMRT proof like so. If we choose a proper fan, which fan is so if fan is the Lie algebra of GQ, where GQ is the, if you regard E as a homogeneous manifold, G is just a group acting on that. So if this we choose this is a fan, is a proper. I mean proper, I mean some proper conditions. We can construct a toroidal compactification gamma by D toroidal, and this toroidal compactification depends on the fan we choose. So in this case, and this space compared to the Baily-Borel, so as you see, Baily-Borel is canonical, but in most cases, the toroidal is not fan. But however, by this choice, we can resolve the function singularities in Baily-Borel, so which is smooth if gamma is neat. And of course, like the projective, of course. So as well, like so, there's a very nice theory, like so, very nice result on the reduction theory that builds such a fan for some classical cases, for example, the circle of a space or realized as a modularized space of polarized abelian varieties. So in both of these compactifications, as you see, we are compactifying the resulting locally symmetric varieties, but we also have the period that can be extended to the boundary is the image in this property dark space. Yeah, but however, as you see, both of these classical condition series work only for the locally symmetric varieties.
But there are several toroidal compactifications, right?
Sorry?
It's not unique, the toroidal compactification.
Oh, of course it's not unique because it depends on this fan. Okay, yes, sure. Yeah, not canonical. I should say mostly not canonical. And depends on the choice of fan. Yes. Okay, so the boundary asks, like, so we have this very nice series for the classical cases, which like so. I think that both of these series has aged like so almost more than half a century. So it is natural to ask, do we have some like so natural way or say like systematic way to extend any period map, even if it is non-classical or say this does not have any locally symmetric varieties? So this is what I really want to talk about is by Haohua Deng theory. So Kato-Usui theory, I believe, like so they announced this theory at the beginning of the century, but the book, like so, the book, like the representing the theory, like is like so, as I studied book, is published in 2009, and they have some another series of papers modifying this theory and even for mixed theorem. Okay, so the theory is aiming at extending a general period map of general height. And so the result is what you expect from the theory is that if some certain satisfied, we will have S, let's say ext, which is extended space, mapped to quantum large space. Let me temporarily run on as KU. So this KU is the Kato-Usui style extended space of the original quotient theory. Okay, so what is Kato-Usui space, right? So this is the first problem. So to understand the Kato-Usui space, we might have to begin with very classical result from Schmidt, that is the Schmidt's equivalent orbit theorem. So recall that suppose we have a local period map. Let's say this is K to gamma sigma by D. Here, this is a local period map on the puncture disk, and its gamma sigma is generated by T1 to Tk, where Ti are the function of period. So now we can always say this. Otherwise, sometimes you may have seen this times another function, non-puncture disk L, but we just in this case by allowing some finite moment. Okay, so one of the first classical result about this setting is the Borel's monotone theorem. So all Ti are quasi-unit. And also, of course, if we have this, then we can just do a base chain, find a base chain to make sure that all of them are unique. So in this case, we can just assume that Ni is a log Ti, maybe something like 2 pi I, no 2 pi I. That's log Ti. So this monotone logarithm, and based on this monotone theorem and all of these, we have this monotone logarithms. Schmidt's equivalent orbit theorem says, we can have some because D locally, we can have some Hodge filtration. So what he stated is that after untwisting all the Hodge filtration, we can extend it along across the boundary devices. So, okay, so let me say he says, there exists ln, which is the limiting Hodge filtration. Let's say in this case, I just write down what is the case for the central point. Let's say just 0. In D check, which is the compactor of the original domain, such that, sigma is generated by this and all of these multiple logarithms, and this at ln is the logarithm. So this is the classical result from Schmidt's equivalent orbit theorem. So it says so for any boundary, here I just obtained the central point, but if we come to some lower, some other boundary stratas, then we just modify this K, modify the sigma by the appropriate strata corresponds to that point. So this is an equivalent orbit. There are several remarks on these classical results. So let me write it down. So the first is that this F-min is well defined, but only up to a choice of coordinates. So this is well defined only up to a choice of coordinates. Which means so indeed, we change the coordinates, these local coordinates, this F-min will change, and the change is by rescaling by some coordinates of this given form. However, F-min is not well defined, so it's not defined. But what is not defined is Well, first is the Newton orbit. So let me define as the space this theta sigma. So this Newton orbit is well defined. And the second is corresponding to Newton orbit will have a naive limit or the reduced limit. So it depends on the different literature. Some people call it reduced, or some other people call naive limit, which is f infinity. So f is the like a Smith coefficient. F infinity is the naive limit. So this is defined as the lim yi times infinity exponential I y n I f lim. So clearly, this is also well defined. It's well defined. And also, because like so, you choose different coordinates corresponds to this scale by this in. But in corresponding unit structure corresponding to the orbit, in I are all -1 -1 vortices. So this means the gradient pieces. So let's say the corresponding unit structure have graded pieces, as well as because it's -1 -1 level 2, so it does not affect the graded pieces and level 1 extension data. So so let's say how to say this. So we have this well-defined objects for this local field map. Well, inspired by this, so we can the Kato-Usui space is exactly the space of movement orbits. So of the point orbits. So let me write down for the local case. So if we let d sigma be the space now, tau Newton orbits, where tau is a space of sigma. So this is the Kato-Usui space about the orbits. So it's clear that if we take tau is 0, then this is exactly d field. But we are adding some other Newton orbits, right? So when tau has positive dimension, we are adding some Newton orbits. So here we'll have the Kato-Usui's construction is given by the original period map on the punctured disk to gamma sigma by d sigma, and this can be actually extended to gamma to k, where we are mapping this guy to gamma sigma by d. Oh, this is one sigma. Sigma is here. And more precisely, this is exactly, well, gamma sigma by d union all these boundary components corresponds to the positive dimensional phase. So this is tau sigma by gamma, right? And gamma, let's say tau, b tau, where b tau is the set of tau Newton orbits. So this is the local construction of Kato-Usui space, and yeah, it's kind of it is a generalized domain to the space of Newton orbits. So maybe on to the local case. So what about the globe? Right, we have more than one local structures. Oh, sorry, first time use this. So B tau, so tau is the phase of the sigma, right? So this is like, so let's say this sigma is the collection of sigma phases. Your sigma is a cone, right? We are taking the collection of all these phases, and tau is in this, but I say multiplied by this gamma sigma. It's a equivalent class, so we just take one member point is the equivalent class, and gamma tau is like we restricted the subgroup fixing this tau, is each phases, and B tau is a phase of tau nanovolts. So for example, in here, the whole sigma is like K, so we choose the one of the phase, for example, N1 is tau, then that tau is exactly the space of N1 nanovolts. So any other questions or comments? Okay, thank you. So now let's go to the global setting. Okay. So what about global one, right? So with global we have this S phi gamma by B. So if we extend this global, so maybe you want to ask, can we just take this, because like so this here map as a constant projective, so can definitely find a color, and of each color, each element in this color, it is isomorphic to a product to this n. You will this, right? So they are the fundamental structures. So it is natural to ask, can we just right? So we just like so example each local structure and patch it together. The answer is yes, but with some conditions, right? So how to patch all of this together without like so destroying the nice properties or say getting something completely nonsense. Okay, so let's see. To patching or local constructions to a global one, we need a notation of a fan. Or say, and to be more precise, is gamma strongly compatible fan. So what is this fan? So this fan is defined as, first, when we say, suppose sigma is a collection, is a collection of sharp cones in the Lie algebra, let's say Q, the rational cones, and this collection, all of these cones in collection is generated by nilpotent and commutative elements. So these are like so, for example, like so for the Schmidt or the theorem, the local commutative cones are this. So now we are assuming like so the collection of such cones, and this is not this order collection, right? Because I'm not saying like this it has any nice contemporary property. So now we say it is a fan if so this collection is a fan if, well, sigma in this collection means any phase of sigma is also in this collection. The second is for any these two members in this collection, we take their intersection must be a phase of both. Right, so it has some nice polyhedral composition. It cannot be an arbitrary length, so arbitrary collection. So this like control is from the Fourier property, but also this is like the most important part is actually gamma strongly compatible. So what does this mean? So this is a fan. It is gamma strongly compatible well, if the following two conditions are satisfied. The first is that if sigma is in this collection, so does the adjoint action of gamma and sigma for any elements in this group gamma. So this means this collection should also close under gamma adjoint gamma action. The second is any sigma in its collection is generated by the logarithm of gamma intersect with the exponential of this sigma. So which means like so if like any cone must be of the form. So if this is a cone, then the generator always generator must be of the form of the logarithmic. So this is the condition of gamma strongly. So this is a really strong condition, and this term plays the central role of controlling the geometric properties of the Kato-Usui extended space. So basically speaking, if you don't have this fan, I mean, this Kato-Usui space can be constructed without this condition, but if this collection is not a fan, not a gamma fan, what you get is something not possible. But this, so if we have this, the Kato-Usui space, well, let me write down the series for in the theory. So now I let B is sigma be, well, sigma, the collection of sigma, you can always for any sigma in this collection. So just take this fact, you have this collection and take all the any components and take the segments, you will always and the union them together. Okay. So what is this? The Kato-Usui theorem A, actually there are two central theorems. So KU's theorem A says this. Well, the first, if sigma is a gamma strongly compatible fan, and if gamma is neat, this extended space, right? We are constraining this gamma by B sigma. B sigma is this guy, and we take the gamma action. So this space underneath a very special structure called the logarithmic manifold. And particularly it is household. So I will talk about this, what is a logarithmic manifold later, like by giving a rough picture. So this tells you that it's particularly when this like a sigma, actually it's just comes from a single cone with, I mean the local construction, right? A single cone and its faces, the local construction is also a physical logarithmic manifold. And the second is we have the local construction right? So we take the cone and its faces, we take the local construction, and this, we use this notation. So you may already guess that is the open value in the category of logarithmic manifold. So this gives a very nice structure of not only the ambient space, but also the relation between the global and local structures. So this is theorem A, and they have the second central theorem, the theorem B. This says that for any S in gamma by D phi, so this is a general theorem, and gamma is something like say gamma is an arithmetic product, just like something GZ contains the modules. Then, if sigma is if we can find such a strongly independent band corresponding to gamma, then we have the natural extension. So S, well, from S bar to phi bar, we have such an extension to the Kato-Usui space, and this extension is unique. Yes, unique, and it is a multiple of logarithmic manifold. So as itself can also be is a special case of logarithmic manifold. So this is another central theorem of Kato-Usui theorem. Okay. So maybe it's time to explain what is a logarithmic manifold and why we care about this, right? So I'm not able to give the very precise definition at this time because the precise is very hard. I mean, very complicated. I believe it costs like 20 or 30 pages to completely build a theorem for this. But let me just give you an example of how this logarithmic manifold is. So, like a manifold can be understood as normally charted by contracted auto sets of some given combination. So, what is logarithmic manifold? So, what are its local charts? The local chart of a logarithmic manifold is something like. Well, for example, if this is B2, and now we just expanding one of these axes. Suppose this is the axis, let's say x equals 0. We expand this single axis, but we add back a single point 0. So this is a standard model of a logarithmic manifold. As you see, so this logarithmic manifold is not analytic. Yeah. But however, the good point about this logarithmic manifold is this is stratified by analytic subsets. So which means though we cannot consider the globally global analytic structure, or say any point we can consider is tangent space corresponding to the whole logarithmic manifold, but we are still able to consider differential structure stratas, right? So strata. So in correspondence to our pyramid case, if we have such an extended to is S bar, we are still able to talk about infinitesimal extended pyramid on each strata, right? We cannot draw different strata, but we can still consider the differential structure along each type of different objects of the pyramid. So this is the good point of the logarithmic manifold. And also this is a conjecture, but very rough conjecture. The image, it's just informal, so I should say informal. The image of this phi extension in this gamma sigma. So this is a logarithmic manifold, but this guy should have much better structure. So the most optimistic guess is projective, right? Because we already know the image of a pyramid is positive projective, so it is the most optimistic guess is that taking a closure in this Kato-Usui space gives you something. Yeah, I know this is just normal, but it might not as good as this, but we can try. Okay, so any questions about this main theorem and also the model of the logarithmic manifold? Okay, so okay. So let me I want to do this. So let me place this. I want to give you an example on the application of this Kato-Usui space. So this example is worked out in 2020 by Dorado, Kerr, and Schaeffler. And also, like so now, Dorado and me is trying to generalize the example explained in the original Dorado, Kerr, Schaeffler state. So, but this is work in progress. And this is in 2020. Yeah, okay. So this example is considering like something that N08, because like this is the example using the Gaussian Schaeffler, so I just use this complete example. So that N08 be the moduli space of 8 order points on P1. So for this modular space, we can like know like so be a stable pair compactification. So consider is compactifications from stable weights of a stable pair. So there are like so for example, so if we like this is there are 8 points. So if we are associating a weight, let's say just like so 1 place. 1/4 is just the even weight. And 1/4 plus epsilon is again even weight. And for some very small positive number epsilon, we associate the corresponding stable pair compactification. We'll have n0. Let me just like say 1/4 plus epsilon and n0 1/4. So this is indeed is called like so current blow up of the segment. So this is the current blow up along the cusp. Okay, let me write in bar because they are indeed magnifications. So about these two spaces, the Lee-Mostel has a very classical and nice result, says that this new 1/4, this space has the natural isomorphism with the Baily-Borel magnification of the complex ball. Or say like this is exactly also this is arithmetic group, and this is indeed more precisely as U15 as U1 as U5. Yes, so this is a very classical result from Berlin and Moscow. Well, and in Gaussian-Schaeffler, they proved that, well, after this current blow up, we have another isomorphism. This isomorphism is still constructed from the complex ball, but this is the toroidal. So recall that, so in this case, the toroidal compactification for all quotient is canonical. It does not compare. So in this case, yeah. So this is a very nice, beautiful result on, and we'll be looking at like so the model space of the points of P1. So what is good? What is nice about this? So okay. So recall that this is classical, but toroidal compactification, right? But we can also use the Kato-Usui theory to explain this modular space. So indeed, you can use Kato-Usui theory to construct this extended period map to the toroidal compactification. So indeed, okay, so first, the moduli, so first we need to take a look on the complex space and say, okay, right? So if we regard N08 as resulting auto set in this corresponding weighted stable computation, 1/4 plus epsilon, we'll have the boundary devices giving non-finite monotony, or say infinite monotony. Well, there are 35, let's say KSBA device, KSBA exceptional device. So these exceptional devices exactly from this Haohua blower, you know, the other communication is given by the weight 1/4. So this product gives you 35 exceptional devices, and these exceptional devices are exactly all devices gives you infinite monotony. So we just let denote the monotony equivalent as Ni. Well, in this case, the Kato-Usui communication. Oh, I should talk about period, right? Sorry about I didn't talk about period. So the period now is the original period at one N08 to this quotient is given by, so you can understand as a homogeneous local system. But the way to explain that I prefer is we take a family of curve given by the fourth color branch of P1 branch alone is 8 points. So these are F coordinates, and we take the closure in the weighted projective space 1, 1, 2. So this is a family. This is a family of smooth projective curve, and this configuration lies in the origin N08. So N08 is distinct. Right, no, the origin N08 should be distinct ones. And for this curve, let's say this is just a CX. Is this curve? And the period gap is given by phi, is given by the, okay, so I should say phi x is Cx, well, C, but however corresponds to some specific character. So because this is a branch color of P1, right? So we have the natural finite automorphism given by Y mapped to Y IY. So I denote this map as rho. So this covering map, it is a finite automorphism, so it has its eigenspaces. So if we choose the first homology and consider one of its eigenspaces, and one of its eigenspaces, we'll get the period map, which is a CVHS, right? CVHS over this N08. And with the image in this quotient. So yeah, so I should explain this period map at the beginning. So the Kato-Usui's communication in this case is exactly given by N0 plus epsilon mapped to this phi, let's say Ku, gamma 1/4 B5. This is the original one, right? Original period quotient. The boundary component is given by, well, gamma n, Bn, we union all this where this n is in the gamma 20 plus of sigma, where sigma is all ni and their gamma conjugates. Yes, so this is the construction of the Kato-Usui's communication in this case. So in this case, we need a fan, right? Gamma string metal fan, and this fan is exactly constructed by just choosing all these ni. They are only one-dimensional cones. So you have these one-dimensional cones, you take all their gamma conjugates, you definitely have, right? So just take this fan, and we can construct it. And this definitely gamma string compatible, as you can verify this easily. So this is the Kato-Usui's construction. And indeed, this space is exactly the toroidal space. They agree. So indeed, like the Kato-Usui proved, like so their construction in classical cases if choose the same fan, right? So and choosing a Kato-Usui fan is indeed equivalent to choosing a fan in classical toroidal compactification, and they resolve the same space. But however, a very good point to choosing analyzing the Kato-Usui's communication is that the original toroidal communication has left very few information about how this might look like, right? So for example, we have a point in this space, N0, this compactified space of pointed curves. What is the point being mapped to in the toroidal communication? So this is very hard to visualize in the classical settings. But however, in Kato-Usui settings, this is very clear, right? Because this Kato-Usui space is constructed from this. And it's just constructed from the corresponding orbits. So indeed, in this curve case, the image can be constructed from the Abel-Jacobi map of a curve, of the single curve. So this is one point. This is one, like so in this case, like so analyzing the Kato-Usui space gives us much more information than analyzing the original toroidal. So any questions or comments? Okay, thanks. All right, so yeah, like so only 10 minutes, so I have to. Yeah, I have to be very quick. Okay, so I haven't talked much about these examples and construction of Kato-Usui space. So now we're going to ask how you can apply this to a general period map, right? Well, as you might have already seen, the most significant technique for you to apply the Kato-Usui theory to a general period map is to construct a map. And this proof it exists. We don't know if it exists. So, for example, if this is a general period map, and we take all these local monitoring points, let's say this sigma 1 to sigma k like this, right? All is a collection of all the local monitoring points. Well, the sigma must contain the adjoint gamma action on all these points, right? Or in other words, like so, we just have to prove this collection is a fan, right? We don't know if it is a fan because, like so, if any of the sigma has dimension greater than 2, there might be some very nasty intersection between them. They are not satisfy the condition of the fan. So this is one of the most significant technical difficulties in constructing the Kato-Usui implementation for general cases. So let me talk about the first things that Kato-Usui, originally they just have a very ambitious conjecture that and original is that like for any period domain, like such as D, there exists a fan, let's say because that's sigma D, okay? In this, the lead algebra is the rational GQ, such that any period map of this type can be extended to S phi to the Kato-Usui space corresponds to this single fan. So in this case, they call this is a complete fan. So this is originally what they expected, but well, this is way too ambitious. They want to use the single fan to make the extension for any period numbers. So this is wrong. And first, in 2008, indeed, before their book published, one of their students, Watanabe, proved there's no such a complete fan for this type 222, which is almost the simplest non-classical cases. So the second is that in my thesis, there's no complete fan for any ABA G greater than A greater than 2, or 1 H1, H greater than 2. So this is a much larger classes that you cannot expect in this very ambitious goal. Okay, so but this is okay, so I should say this completely can exist in the classical cases, right? Because in the classical cases, well, extended constructing this like some universal extension is equivalent to extended like a single VHS, which is D itself, right? Because in the classical cases, D itself is the rational structure. But in non-classical cases, this is definitely wrong. So this is not a successful analog in the non-classical case. So, well, what is a successful analog for the non-classical cases is that, well, at least like so, in my opinion, and also my work shows that the successful analog for the non-classical case is we are finding a span for a single period map, right? So we are considering just a single period. Here. We are considering just a single period map. We want to find a fan sigma, let's say this is 5, right? Because this 5. Here I use C means I use any value here that is the image in the quotient of the C, but now I only say this fan only works for this single period map. I use this 5. So which is gamma strongly compatible such that we can find a Kato-Usui extension. And indeed, like so, this is only a partial extension. Okay, I should say this. So, okay, I should say this. This is just an extension. I don't even want to extend all of these compatible. Okay. I don't even want to extend all of this as far. I just want to take some boundary structures, right? If we can successfully extend this map into Kato-Usui space over some non-empty boundary structures as we have written progress. So this is our goal. So how about this, right? We are sending just only a single period map. So also in my thesis, I just let the following, maybe as far as I know, it is the first known example that there exists a family of Calabi-Yau threefolds of type 1, 2, 2, 1, which is given by this S, well, S bar is just P2. And this is constructed by Hosono Takagi. Such that, so this is an S, I would say this is P2 minus some discriminant locus. Yeah, I just said P2 minus the discriminant locus, and I mean recommendation is P2. What I proved is that under some finite resolution, which corresponds to some finite subdivision of local monetary forms of this period map, we do have a Kato-Usui extension. So first, I should say, as tilde, right, as tilde to, and also gamma 0 in gamma is a finite index neat normal subgroup. So this can be always done. So I should choose a finite subgroup which corresponds to a finite base change of S. So we have finite base change of S, and finite blow-up means we still can also describe the nice properties on the base S. Yes. Yeah. So we indeed have such a Kato-Usui extension. So this means like so after some finite procedure on the base, we indeed can construct such a Kato-Usui extension. Okay, so this is the quick example given by this is that such a Kato-Usui extension exists. So let me just say the final notes about some work in progress. So this is because like so in this result it's only about right a single example, right? I just made to prove that Kato-Usui's theory is empty. It's not empty, sorry. It's not empty, but what about how much can we use this, right? How much can we generalize this? So this is work in progress with toroidals. So of course, like so we are trying to extend, like so find more examples, then we can use a Kato-Usui extension, right? So this is like so for S to phi comma by D, and for some certain degenerate types, let's say I extend means extendable, we can actually have a Kato-Usui extension to X extend to comma by D, something sigma extend. So indeed, like so what we are trying to do is that for a period map and boundary couplets and boundary multi-couplets, we have a corresponding limiting for structure, and they are different for classified by types. So for some of these types, we indeed can find such a fan and construct a Kato-Usui extension. But however, at this point, we are only able to do the same limitations to all the constructor types, but now only like so a very small amount of very high degenerations that accept our implications. So for example, currently we only know is that like so the type 1 degeneration of the color EL. This is like a very minor degeneration. Like so, in many cases, this is almost it has some very common properties with the classical cases, but it's still classical. So this is still progress. And also maybe the Hodge-theoretic. Hodge-theoretic is the most degenerating in terms of the Hodge-theoretic language, but only of type 1 to 1. So it is either generalized result thesis. But for some many other types there are still some substantial difficulties that we are trying to solve. But like so, yeah. So anyway, we still have some non-empty progress. Okay, so same coefficients.